So, it's nice to see a nice crowd after 2 years of pandemic. You're beautiful. So today we're going to talk about similarity detection and how we use it in integrity. Integrity as a way to ensure that the website is a safe place, that people just maintain an integrity of place. The outline of the presentation is as follows. We're going to outline the problem, then how we use automation and similarity detection in order to achieve what we want. The current technology that we use for images, which is the vector search. Then we're going to discuss in depth what is the actual technology, the embedding, the vector embedding makes possible to transform a picture into an element of search. The current platform offering that Meta puts at disposal to allow other people to crowdsource all of their findings into a centralized place. And last but not least, what we have of open and free that you can install in your own, you can deploy in your own site to benefit all these technological findings. So the problem is that any big platform bears the responsibility to ensure it's a safe place to serve. No matter what, also the law says that you have to make sure whatever the user posts, you are ultimately responsible to make sure that everybody is just not exposed to things that will violate your community guidelines. Meta has almost 3 billion users, is slightly less than the world population. And although the vast majority of our users follow rules, some fringe bad actors will always be present. And at that scale, fringe means tens of millions of bad person creating a lot of problems. And when I mean issues, problems, I mean child exploitation imageries, non-consensual intimate imagery, which is a way to say revenge porn, adult sexual exploitation, people forced to perform sexual acts in front of camera against their will, terrorism, violence, whatever. And just to give you a couple of numbers, Meta publishes a transparency report quarterly about what we do to ensure that platform stays safe. And on the second quarter of 2022, we removed the 38 million of adult sexual exploitation pieces of content taken down. And it's just for this category. Child exploitation is not so huge, thank God, but also there are other like violence, terrorism, and stuff. That accounted for the 0.04% of viewed content worldwide. And in case you were asking, 97% of this content was proactively taken off, even before people could even see it. The remaining 2.8% is a user report, like, hey, I found this. And we take that down also, and we also add to the data banks just to make sure that we are not forgetting about that. Sometimes there are false positives because it's just unavoidable. And 500,000 was restored upon user appeal, and we restore accounts and mostly accounts and the pictures that were banned for. It goes by itself that the sheer volume of content, the huge scale, the problem that we are facing, requires both automation and also human review to ensure either accuracy, both accuracy and also consistency. Because it will be a problem if we had 1 million people clicking and making decisions, and what is violating for one is not for the other, and vice versa. And so, and we cannot just also just employ automation, because otherwise we will have this very powerful site decapitating everybody, also innocent users. So the role of automation and similarity detection, the tenet is that a lot of the things that happen online are things that are being repeated. So are things that already occurred in the past, like people posting a picture of some shooting, some mass shooting, for example, like the Buffalo or the Christchurch, gets taken down, and the 10 more accounts spawn and post the same things. So it's much, it's very efficient to reason in terms of let's just redo the things that we already found out it worked. We employ automation to scale, of course, handle the scale of the problem, and to consistently repeat a decision that a human reviewer has already vetted in the past. So we tie a content to a decision, a violating content to a decision, let's act upon this. And we tie the decision to the actions. Let's just repeat this action every time we meet a piece of content that triggered this same decision. We do that for videos, for pictures, and also for text. Today, we'll be mostly talking about images because the techniques for video and pictures are somewhat very similar. Text has a completely different array of techniques that we'll not be presenting today. So, a way to, if you want to achieve similarity detection, you have to come up with a way to achieve similarity first. So how do we compare to pictures? Of course, we are not be doing pixel by pixel comparison. We want to be much faster. A way to do that is just, okay, let's just MD5 hash all the pictures, or SHA-1 all the pictures, and then we store them somewhere in an indexing system. And whenever a new picture comes in, we just recreate the hash, and if it matches, we just ban, right? Well, that doesn't work very well, because the cryptographic hashes are not resistant to resizing, rotation, one pixel alteration, the hash changes altogether. Instead, we can really benefit from local hashing, because it allows for similarity measurement. Like you change slightly one piece, one portion of the image, and the hash changes a little, but not completely. Then you can reason in terms of distance between two hashes. So you have to find a way to turn an image into a vector, and then you perform a vector search. Whenever two vectors are very, very close beyond a certain threshold, then it's probably a match. And just in case if you're asking, this is your base SD architecture. You have more or less all the architectures share these four stages. Observation, an image has been generated, usually a push event like user uploaded something. Then you have the representation phase, in which you hash the image to a compact representation. If you're indexing, you store that into your index. And instead, if you are at inference time, like an event, someone uploaded something, you search the index that you've built with representation. And in case you have a match, you action upon what you decide what to do with the match you got. Usually, the idea is that this is very close to an image that I already seen in the past that was banned, and also the account was taken down. Do the same to this user. So, first free piece of content, Facebook has released a library, which is FICE, the Facebook AI Similarity Search Library. It's a library to do similarity search over a vector of dense vectors, so vector floats or integers, for example. It's you can think about it like a C++ version of Lucene, so you index stuff, puts that in a very big space, and you can search in this space very fast. It supports CUDA, so you can use your GPUs to search. It's basically an index on steroids. And it's C++, but it has Python bindings available. And it scales almost linearly. You can really index 100 millions of pieces on a single machine, and it just handles them really. It doesn't need to saturate all the memory. So it has a very good optimization properties that makes it a good tool. And you can go and download that on GitHub. Today, we are also mostly referring to with the perceptual hashing. This means that we are reasoning in terms of colors. Colors in the images, shapes. We are not reasoning about what's happening inside the image. That is the semantic hashing, which we are not going to talk about this today. Perceptual hashing just captures visual similarities, and it's very nice for a use case because it exactly does its job. So, you might think that we are all talking about machine learning systems that come up with very clever representations about our pictures. And I'm asking, do we really need a ConvNet for that? Do we really need to employ GPUs? Well, you already said that it's on CUDA, so perhaps that's a nice hint. But absolutely not. Most of this technology is like a hashing technology. So they just compute or represent a mathematical transformation over the image. And it's really fast, and it's really cheap, and it can be executed almost everywhere. So a little bit of history. The first very notable example, it comes from a source that nobody will have thought about. It's Microsoft. In 2009, Microsoft invents PhotoDNA. PhotoDNA is the first algorithm employed in fight against exploitive images of children. So, pedopornography. It transforms a picture into an hash of 144 unsigned integers on 8-bit representation. It's proprietary. So Microsoft licenses this to any non-profit or any organization that wants to fight exploitative imagery of children. It gives you a license you can use for that and nothing else. But I cannot disclose the details of how that works. It can be used only for that. But Microsoft donated the PhotoDNA to the National Center for the Missing and Exploited Children, the NACMAC. It's this American no-profit that basically acts as a coordination center in the global fight against this phenomenon, and shares this library with anyone that wants to integrate. This, I cannot talk about how this works. This is the only moment in which I will say something like that. But we can talk about an open source counterpart that almost 10 years later, Facebook releases PDQ. PDQ stands for a perceptual algorithm using discrete cosine transform and gives a quality metric. It's a very, very bad acronym, but we need a 3-letter acronym, so this is that. It creates a 256-bit hash. Uses Hamming distance to compute the distance. It's really fast. The compute overhead is negligible compared to discrete. Can tolerate some level of adversarially. This means that you change the image because you want to fool the systems in that this image is not something which is well known. PDQ can resist a little to this manipulation, but not to all of them. And it's used in stopncii.org. It's a website where people, in case you have a fight with your ex-fiancé and he's threatening to publish your intimate imagery, you go to stopncii.org, you upload your intimate imageries, fingerprints get taken, original images get deleted right away, of course, and these fingerprints are shared with partners that, okay, if I am going to see these fingerprints in my website, my platform, I'm going to take them down. So it's a crowdsourced effort and uses PDQ for images. How does that work? So PDQ hashing is you optionally scale down to a square image. Okay. Then you compute the luminance. Luminance is the idea that you take the pixel that contributes most in the RGB channel. Instead of putting black and white, you use the luminance. It's just another procedure. And the idea is that luminance gives you better information about what was the channel that was contributing most to the color or to the light in that place. Then you downsample to 64 times 64 using a blur filter. And the idea of the blur filter, a tent filter, is that it gets the most significant value in that region. Because if you keep convoluting a pixel with your neighborhood, what you will have in the end will be the highest value. So you obtain a representation which is compact and retains the most significant information. Then you divide the images in 16 times 16 boxes, each one 4 by 4 pixels, and you calculate a discrete cosine transform of each box. The discrete cosine transform, so the box is that the 4-bar color there. You see that the grid with a lot of wobbly images, that is a discrete cosine transform. The idea is that any image, any signal can be represented as a sum of cosines, the sum of cosine signals. You only take the signal, the most significant one. So it's a form of compression, actually. And you take the most significant coefficient for the biggest cosine you have, and then you calculate if the median is above a certain value, then it's 1, otherwise it's 0. So you get this 256 in an array of 0, 1, 0, 1, 0, 1 in case this pixel were a high luminance or a low luminance. The DCT provides a spectral hashing property. Identifies what is the point in the images that contributes more or less. You have an hashing space which is 2 to the power of 1 to 28 because it's half the hashes, because half is always 0, half is always 1. To search, you just do a vector search against what you've just created. In case we want, we can use partially the same technology to do video hashing. And this is another, comes all in almost the same paper. The TMK is the temporary matching kernel. Is a way to use the PDQ creation to do a video similarity detection algorithm. It produces pixel length video hashes. So your hash stays the same length, which is like 256 kilobytes, if I'm not wrong, even if your video lasts for 3 hours or 30 seconds. It just produces a pixel length, so it's really nice. What you do is that you resample a video to 15 frames, then you compute the PDQ without the 0-1 quantization, so you keep the float numbers. That's why it's called PDQF, PDQ float. And then you compute the average of the all descriptors that you have within various periods of cosine and sine. Why we add the cosine curves? Because a cosine or a sine adds this wobbly movement that tells you whether a frame is before or later in the near surroundings, the near neighborhood of the frames. So in case you have like 10 pictures, you add this cosine signal, you know this picture is before this one because you see the cosine curve which is going up and going down. And it's a nice uniqueness fingerprinting time signature algorithm to add a cosine. So you compute the average of all the frames, the PDQF for all the frames, with various periods, various sine and cosine, and then you pack them all together, and you have these like 5 or 6 averages, and that's your PDQF embedding. Searching is just, you compare first the vector 0, which is the average of all the frames, and doesn't retain the temporal signature. Then if there is a match, you compare also all the other vectors at different periods, which are this is the level 2 hashing as the time signature. And so you can really be sure that the videos are really the same, because if you find the same averages with the same periods, it must be the same video. It's nice that it's resistant to resampling, because you always resample. So in some way, if you vary the frame rate, the video will change. An MD5 hash will change, but this one is not fooled. Hashing is really slow, because you have to do a transcoding of all the videos first, and then you have to read all the frames and compute the PDQ for every frame. But search is actually very fast. Another nice hashing technique that we have is the video MD5. I said that we will not be using crypto hashes. I lied. We use crypto hashes, but just for videos. This because if you take an MD5 of video and find exact copies, it's really cheap in this way. A lot of actors just post unmodified, repost unmodified content. They're not going really through the hassle of do a encoding just to try to fool the systems. They just try to repost again. So the MD5 actually works, and it can be done with vector search if we use the bytes for the MD5 algorithm. And it's used widely in stopncii.org also. In 2022, Facebook has released the video PDQ, which is a different algorithm from the former one. Hashing is we hash every frame to a PDQ hash, and we just pack the list. It's much bigger, is not slower than the other one, but it has a nice property that we just have to search for individual frames. So we treat the problem as a bag of word approach. So we just put all these frames inside an index library. Then we search and we take all the candidates and we do a pairwise comparison. If the pairwise comparison is successful beyond a certain threshold, then it's a match. And also this you get for free, and it's released along with the PDQ, along with the TMK PDQF. All this is available inside the Facebook research GitHub repository. What do you do once you have these hashes? So your platform is computing the hashes, but it's the first time that you see this content, but perhaps other actors have already seen this content too. Well, you upload them to the threat exchange platform. NECMAC shares the PDNA hashes I told you with all companies that are asking for them. So can you please tell me where this picture that someone uploaded is a match in NECMAC? So I already know that this is something I should call the law enforcement. Meta does the equivalent, but for the PDQ, because it's much less friction to adopt PDQ compared to the PDNA. There's a team, the Internet Safety Engineering, that builds and operates all this service where anyone can upload fingerprints, and so you can crowdsource a big graph of matches. Expose REST API to access and post new data. Has multi-language clients. Uses PDQ, and users can also download the data. You are not forced to stay online, stay connected. You can just request for a dump of the database, and you can search it. And you find all the data and all the APIs at the GitHub page. In 2020, Facebook also has released its most advanced algorithm to spot similar images, the SimSearchNet++. This is a neural network, and it is capable of facing adversarial manipulation that the other embeddings just are not able to. Unfortunately, SimSearchNet is proprietary, so I cannot really talk about that. But we have a cousin product, SSCD, the Sim Search Copy Detection, or Similarity Search Copy Detection, which is open source and free. So I can really talk about that. They are somewhat related in some technological principles, so I can really talk about this. So this is a PyTorch-based model. So the problem that this, which is a state-of-the-art product, is trying to solve is what happens if I take a picture and I put a caption on it, altering so many pixels everywhere. A PDQ or a PDNA hash will be altered dramatically. But is there anything we can do to teach a computer to just ignore all the captions, all the rotations, all the jitters, all the cropping of the image? Yes, there is. A person is able to do that, so we can teach a computer to do that too. So models and code are available. What is not available is the training data that we use to create the model, of course. For those which are into the deep learning, it's a ResNet 50 convolutive neural network. And the novelty of the approach is that it's based on R-Mac vocabularies. A regional Mac, for those, how many of you know how a convolutive network works? Raise your hand. Okay, fine, very good. So it's a network for the others that looks at the image, looks at portions of the image. Each neuron looks at a different portion, and then they pass what they have understood to a higher level series of neurons, the higher and the higher and the higher, until the last layer of neurons has a very wide overview of the whole picture. In this case, we are using the maximum activation of all the channels that we have. So we take note which are the regions of our Karnaug maps for every different channel, which across all channels have the maximum activation. If you have 10 channels and that region across all the different channels, all of them you have a maximum activation, that means that that area is an area of interest. So we use these areas of interest as a word in a vocabulary. So exactly when you do the Cousin similarity search for documents, you take all the words, you index all the words, you say these documents has these words, so it's like a vector of words, and then we try to see which are the vectors that have the most words in common and put in the same place. We do the same things, but for portions of the image. So we use the Rmax. The idea is that it's a self-supervised system also. So it means that it's trained to recognize augmented input, and it's trained to match an input to its augmented version. So what we do is that we take the training set, we repeat a lot of augmentation, we add the captions, randomic, we rotate, we flip, we alter the colors. For example, if you do a 1 degree of whitening, you make the image brighter, which is you add +1 to all the pixels in the image, you are altering all the pixels. But in this case, a PDQ hash is capable of understanding the difference. That's a very weak form of adversarial attack, because the PDQ just computes the difference between regions, so it's not going to be fooled. But you can be much more violent and put just a spot color somewhere, and PDQ is going to be fooled by that. Then you do through the CNN. You do a thing called gem pool, which means that you do a generative mean pooling, is a generalization of the average pooling, in case you were wondering. Then you go, and at the end you use entropy-oriented loss function. This means that we want to encourage the network to spread the representation of training data along all different places, because we want to maximize the distance between all the training examples in the training set. So you get a nice uniform search space. When at inference time, you do the same with the CNN, and then you obtain a vector, which is a representation of an image. And the idea is that there is a distance that you can compute between the data set of the reference images. Of course, you can subtract a background data set that was used generally to augment the images. But in this case, what you obtain in the end is that the score of the augmented image is almost the same of the non-augmented version, because it just learns to ignore the places which are not organic in the image. And SSCD is freely available. You can download that and start playing. You find both code and model, as I already said, but not the training data. And by the way, Facebook has also announced an image similarity challenge. You have to determine whether a query image is a modified copy of any image in a reference corpus of 1 million. This is very similar to the Netflix recommendation challenge, when you had to recommend the movies and you had to beat Netflix algorithm. And this is the image similarity challenge, and also the meta AI video similarity challenge, which is two tracks. Generate a useful vector representation for a video, and also try to find a reference video into this very big corpus. And you don't have to only find a video, you have to find a clip, so a sub-portion of a video, into a very big corpus. And last but not least, since the last part of a donor is the tastier one, we have your turnkey open source solution that you can install in your own on-premise. The Hasher Matcher Actioner. HMA is an open source turnkey safety solution. So you just download it, install it, and it starts working right away. What it does is that it scans the images that you want to push towards it. It has an index that is updated with all the hashes coming from thread exchange, but also from yours, and is able to, say, to bind banks, verticals of violations. You might have a non-severe violation or very severe violation, and you might decide that for non-severe violation, you just delete the content and send a warning, or for high severity violation, you just immediately delete the content, shut down the account of the poster, and you also signal it to the law enforcement. You can do that also. And you can configure actions in a backend that are tied to the content that you want to bank into your HMA platform. Can pull violating seeds from Facebook Thread Exchange API, and works on AWS only because we wanted to make a very easy to use thing, and also something that doesn't really makes your bill higher. So we built it on AWS Lambda. So it doesn't cost anything until it runs. Then it runs, spawns a Lambda instance, and then goes down, and you only pay for the seconds that it actually runs. But it's very fast. And there's a Terraform module available thanks to the lovely folks of Internet Safety Engineering. This is how you deploy that. Your infra, you co-locate HMA to your platform. For example, you might own a platform where people have as a chat or people post pictures. Whenever new content comes, the web server asks the hasher, have you seen this? Then the hasher goes to matcher. Matcher goes to the index and says, do I know this? And in case there's a match, the actioner module will just tell you have to define a callback API in your own platform. Like whenever the actioner calls, you are killing this content in your own backend. And of course, you can fetch from external API new content from the Threat Exchange platform. So wrapping up, automation is necessary to be effective. But you will lose precision, of course, because automation doesn't really think. It just does whatever you have configured blindly. Human support is always needed for appeals and also to establish the ground truth. So what is actually violating, what is not. Do expect false positive, because they will happen. You should put in place an appeal process to allow your users to restore the content. PDQ, video PDQ, MT5 and SSCD will provide you with a way to obtain compact representation of high dimensionality content like pictures and videos. HMA provides you with a turnkey solution that you can install on your premise, and search and enforce your integrity policies at your platform. And Threat Exchange provides you with a platform for exchanging representation with other big actors like Meta itself, for example. That was all from me. Thank you very much for listening. Any question?
Yeah, you mentioned it for the challenge, I think. Louder. Oh, louder. Yeah. So you mentioned it for the challenge, finding a clip of a video. Can PDQ do that, actually? Like, you can hear me.
Not loud enough.
So can PDQ find clips of videos of sorry?
Oh,
that's my question, actually.
So you should, you say, perhaps I heard about YouTube, whether it's something that already does. Sorry? Like if the challenge is to find the clips of videos. Yeah. In general, it's possible, of course. And the video PDQ algorithms will hash every frame. So in case you send a very small sub-portion of a video, you will have like 100 frames, for example. Then these 100 frames will be treated as a bag of words. You search the index, you find the video that contained all of these words. So you have a match of all your query frames inside the indexed very long video that has it. And so it's a match. That's how we do. Of course, there are more clever ways to do that. Thanks.
Hello. Not a technical question, but let's see. I was thinking that if you're using such a system to try to prevent digital crimes and such things like that, from a ethical perspective, I was just wondering that I suppose you have such images to compare them, and how do you process those? How do you make the decisions whether?
So I repeat the question. From the ethical perspective, the idea is that, of course, we have to see the images in order to be able to know what's happening, right? Was this the
Yeah,
question?
see, and of course you have to save them and, yeah, I don't know, process them, and how do you handle this?
So this is not the kind of question that I really can answer because it is related to internal procedures. But if we have to compute the fingerprint of an image, there must be a 1 second in which the image is on our servers. It is since the agencies like NECMEC, they share hashes. So you might have an hash for which you don't have a picture, and you have to trust that this hash is coming from a trusted source that has already vetted whether this hash is nasty stuff or not. That's how we actually avoid sanctioning heavily innocent people. So there is a collaboration with the trusted entities for this. When you receive those from an external agent, if those images are on your platform, you already know what you've seen. Thank you.
Can you hear me despite the mask? Can you hear me?
Yeah, thank you.
So I have a question, but first I have a thanks. Because I have worked in this kind of thing, and NECMEC doesn't share any useful data. IWF doesn't share any useful data. Pharos doesn't share any useful data. So I will definitely take a look at the threat exchange platform and hope that it's much more useful. And thanks for that. Now I have a question anyway. If I was an attacker, I could download data from the threat exchange platform and try and run as many filters automatically until I find something that is not matched by PDQ, video PDQ, etc. What's the way to counter that?
Oh, you're asking whether adversarial attacks are possible on PDQ? Yeah, of course. PDQ is a very naive algorithm that just detects the patches of colors. It is actually possible to create adversarial attacks. Just if you think that you alter many pixels in the image, and perceptually for us doesn't change anything, but you might end up changing the most relevant pictures for the DCT algorithm, and will create a completely different hashing in the end. Also, someone has demonstrated an attack, a reverse engineering attack on photo-DNA, like from the project is called Ribosome, and it's a neural network that from a hash reconstructs a very blurry picture. So it is actually possible to do that, but PDQ it's a very simple and fast algorithm. If you really want to combat seriously adversarially engineered things, you need neural networks like SSCD, because it contains so many relations to different parts of the images, and it's much harder to fool. I'm not saying it's not impossible, because of course it's possible. Sooner or later someone will find a way. But it's the usual arms race between attackers and defenders, and it's no exception. Thank you for your question.
Hello. Hi. First, thank you for the presentation. I think it's a very interesting topic.
Where are you? I can't
wanted to link it to, because it's been a bit of a buzz the past few weeks, the generative AI, especially ChatGPT. I was wondering if when you use that kind of algorithm and you scan an image, detect something, is there a level of confidence attached to the result? And can you detect when an image is potentially a fake, or...
I had a really hard time because there's an echo, so I cannot really... can you do it louder, please? It's hard to understand from here.
Hello.
Okay.
Is it better? Okay. Yeah. So thank you, but wanted to link to generative AI, and as I was asking, so when you run that kind of algorithm to detect violence or child abuse or anything else, can you also attach a level of confidence in the response to explain whether it's, to define whether it's a potentially fake picture, or is there an extension to the algorithm where you can link with the generative AI?
I'm not sure about the answer.
So we can go for a beer and I can explain more details. And, let's see.
Yeah, you have a question.
Hi, thank you for the talk. It was very interesting. One more question also. Do you run SSCD in production as well? The deep learning network?
If we're using SSCD in production,
Yes.
can't I reply to this question?
Okay.
We use SimSearch. We use SimSearch net plus.
Yes.
We use this other one because we have written a blog post about this, so I can confirm that we use SimSearch net plus. I cannot nor confirm or deny about SSCD,
That's
but
okay.
those are related technologies, so I can.
That's okay. What does the production stack for SimSearch net plus look like? Like, how do you serve it? It must be pretty hard to deal with the GPUs and
This
everything.
is not a question that, unfortunately,
okay, I'm sorry.
I cannot talk about production setups. I'm sorry.
Okay. Any question nearby? Thank you.
But of course, you can imagine that we do not operate in the vacuum. So if you can think about how we serve results from a neural network, it is something perhaps similar to what would you do if you would have to put behind an API a model.
So I kind of have two questions. The first question is, to what extent I think there are potentially two problems. Intentional mismatches and unintentional mismatches. So situations where perhaps an image has been recompressed or is being cropped or is perhaps another image of the same situation versus situations where people have deliberately deformed the image to try and get around these kind of systems. Do you have any idea of how performant it is against the two scenarios of either accidental or unintentional mismatches versus intentionally trying to avoid it?
So it is, of course, possible to have unintentional mismatches, and I've seen images that were adversarially engineered to give the same embedding. Those are absolutely possible. Again, in PDQ, PDNA, and all the perceptual hashing, which is just a mathematical transformation. You just have to find a way where the input seems the same to the algorithm. For the neural network things, it depends. You can study the code. You can study how it's done. If you can, it is absolutely possible sooner or later, because the adversarial attack on convnets are a reality. So it's absolutely possible. I've seen some mismatches, but usually to perceptual hashes. Usually the more refined the technique, the harder it is to attack, of course. Otherwise, we just will stay with MD5 because it will be enough. Crops. PDQ is resistant to crops. SSCD is very resistant to crops. You can, if you have rotations, I believe also PDQ is resistant to rotations, like flips, but you cannot ask much more than that. Other questions?
Okay. Yeah. Do you have any information about the speed difference between SSCD and PDQ?
Yeah. So the question is whether I have some speed benchmarks in this, for difference performance between PDQ and SSCD at inference time. PDQ is faster than your time to read the image from disk. So it's negligible. It will just compute. It's a mathematical transformation on the pixel. The neural network requires dedicated hardware. If you do that on CPU, it will take seconds, also because the model, I think, is big enough. It's not as big as GPT, but it's a 50-level CNET. So it's, of course, slower and requires dedicated hardware. But it's more precise. It just finds, SSD finds anything that PDQ is able to find and much more. So in case, if you are very curious about, if you are very conscious about, I have to scan this stuff just to make sure they don't come from a ill source, you might want to set up an async process that will take more, but will just batch process all your stuff. If you need a super fast thing, PDQ will not really wait over your server. Thank you. Any other question?
Hi.
Where? Oh, hi.
First of all, great question from my former colleague David, I think, down there. Not even looking this way. But what happens if you get a false positive?
Louder, please.
Sorry. What if you get a false positive match? How do you disregard that in the future without potentially disregarding a real match?
If we get a false positive match, how do we do to restore?
Yeah, how do you
with
restore
HMA,
it and
you
keep
mean,
it there?
or in meta all the day?
Well, just anywhere, like as a concept.
So
what
in
would
meta,
you do?
I cannot really say. With the hasher match reactioner, you have you should provide a capability to your own platform for which you are soft deleting the image, because you have to provide a way, an API in your platform that HMA will call on, where you say soft delete this picture, so make it unavailable, but do not really delete it in case you want to appeal. So you need to provide like undelete and unsoft delete and soft delete capabilities. This is the most, the simplest way and most effective way to deal with false positive. In case, whoops, I did a mistake. I want to restore the content.
Sure, but if you have an image that someone wants to upload, say it's a popular image that a lot of people are going to upload, but it matches a pattern of another bad image, can you is there a good way to make a more precise hash and exclude that and say this one is a false positive, it doesn't match what you think it does? So you don't have to keep undoing.
Okay, if I understand correctly, if the image is popular, so we have many examples and we have many examples of an image which is not bad, and then comes a bad image. Whether we can use the fact that it's very widespread to augment our precision. Is this the question? Okay. Well, really, there's nothing in this presentation that says this, because once you train, the network is trained, and you start serving, and the network will give you the same answers to the same question, to the same query. PDQ or other mathematical algorithm, perceptual algorithm, is just a mathematical function, so will not change it. There's nothing to train. So to change a deficiency of your model, you have to retrain. And you can do a better retraining, and sometimes models are retrained as anything which is still under maintenance. For example, we get new data, for example, and we might want to retrain as any other model also for the spam filters. It's the same. Do we have more room for questions? I think it's done. Thank you so much. You've been a wonderful audience.